Assalamualaikum warahmatullahi wabarakatuh for our lovely lecturer, Dr. Heritan Ahmad. So, our group will going to present the project design of one-story frame for steel and timber structure design subject. These are my group member. I am Sharina Solihim. Let me start first. For the introduction, structural steel is a steel construction material fabricated with a specific shape and chemical composition to suit a project's applicable specification. Depending on each project's applicable specification, the steel section might have various shape, size, and gauge made by hot or cold rolling. Others are made by welding together flat or bent plates. Common shapes include the I-beam, HSS, channel, angles, and plates. These are common that have in structural steel. First, frame. Frame is a complex of column and beams, girders, pedals, and trusses connected to one another to the column anchored in the foundation. Then column. Column is a structural element that is subjected to axial compressive force. Beam. A beam is a structural element that primarily resists loads applied laterally to the beam's axis. Steel trusses. A truss is an assembly of beam or other element that creates a rigid structure. And steel connection. The connection are important part of steel structure and are designed more conventionally than any individual member. So we going to the frame geometry. The method of the frame geometry implement the step pro drawing. This is from side elevation and this is from plan view. So we can go to the structural layout. Structural layout is from the step pro software. Figure 1.1 is plan view of project. Figure 1.2 is front view of the project. Figure 1.3 side view of the projects. Figure 1.4 3D view of the projects. You can see this. So that's all from me. Thank you.
Hello, my name is Noor binti Ahmad. I'm going to explain the loading that was used in this frame project. So as you can see, these are the diagram of load distribution in our step row. This is the permanent load by GK1. This is the permanent load by GK2. This is the variable load QK and wind load WK. They both have the same diagram. The specification of section and selection of applied load from table 6.9 BSEN 1991 2002, we choose H category of roof, which is roof not accessible except for normal maintenance and repair. And then from BSEN 1993 2005, we have a beam in UB shape and column in UC shape, truss SHS section. For the top chord and the bottom chord, we use TUB 100 multiple 100 multiple 6.3. For the internal members, TUB 60 multiple 60 multiple 6.3. Okay, you can see the table below. We have three general type of load, which is dead load GK that apply on the steel, live load QK that apply on the roof, wind load WK that apply only at the top chord. So the GK including the suspended ceiling, aluminium, weight of service, weight of purlin, self-weight of trusses, roof ties, and cladding. So the total of GK 1.46 kN per meter square. The nodal permanent load GK multiplied by 1.35 meter multiplied 3.1 meter, we got 6.11 kN. For the live load QK, the nodal variable load QK, we got 3.14 kN, and the wind load, we got 2.06 kN. The combination of load in step 4, we have using 7 of the selection above, as you can see, SLS QK, ULS minimum, ULS maximum, SLS WK, ULS WK, SLS win, ULS win. So the parameter assigned for step 4 code used was DFF 250 millimeter, minimum required depth 200 meter, tensile strength of steel FU 407,800 kilonewton per meter square, yields stress of steel 250,200 kilonewton per meter square, and the standard grade of steel we use S275. From the drawing that we make, we have span of roof 18.2 meters, spacing of truss 3.1 meter, made of spacing truss 1.35 meter. So as you can see, here is our manual calculation about the load analysis. Here you can see our applied loading, okay, like I explained just now. And then this is our side view of our truss and the plan view of our truss. So we design the load per unit area using this formula 1.0 GK plus 1.0 QK. So we got the answer is Q 9.25 kilonewton. So we sketch the load distribution uh, of 9.25 kilonewton, and the sides of the right and left truss half of the design load, which is 4.63 kilonewton. So that's all from me. Thank you. Roof truss calculation. I have designed the purlins. So this is the data in the step 4 about the critical member of the purlin. So as we can see, the critical member of the purlin is right here, which is at pin number 692 with section TUB 6066.3. So here the calculation of the purlin design. We need to find the spacing between trusses, distance between purlins, termination, variation as follows loading. And then first we need to find the moment WL divided by 8. So use the formula permanent action GK 1.46 kilonewton per meter square multiplied by 3.1 meter multiplied by 1.3 meter. So we got 5.88 kilonewton. Same goes to the QK, variable action QK. We got 3.702 kilonewton. And then combined action W use the formula 1.35 CK plus 1.5 QK. We got the answer 12.47 kilonewton. And find the moment. So the answer is 4.83 kilonewton. And then we need to find the WP, which is use the formula 1.0 GK plus 1.0 QK, and the answer is 8.9 kilonewton. Okay, so from the table 2.7 PS 5750 part 1 2000, use all the formulas ZDV and find the answer using this formula. We got for the Z 15.33 centimeter cube, and for D 54.29 millimeter, and for the B is 20.97 millimeter. Therefore, use the single angle 60 multiple 60 multiple 6.3 for SHS section. So next we need to find the section classification using clause 6.2.5 EM 1773 2005. For the T, we find T, which is 6.3 is less than 14 millimeter. So use the formula using by Fy is 275 Newton per millimeter square. And then we find the answer 0.924. Okay, for the web internal compression, use the table 5.2 with sheet number 2, and then find the limit for class 1 web. We got 6.52, and the limit class for 3 web. The answer is 114.58. So we need to compare both of the limit. So we found that 6.52 is less than 114.58. So hence web are the class 1. So using the MCRD formula, which is MCLRD, we need to find WEL minimum. So find the WE minimum, we got the 17.56 centimeter cube. Therefore, using the angle 60 multiple 16 multiple 52, which is WL 17.8 centimeter cube. So we need to find the check deflection. So deflection using this formula, we got the 5. We could answer is 5.25 millimeter. 11 diffraction using table 8, which is L divided by 200, we got 15.5 millimeter, which is more than 5.25 millimeter. So this purlin is okay, which is deflection is okay. So the purlin design is okay. Thank you.
For the roof truss calculation, I will explain about bottom chord. Then, this is our step pro data. So, as you can see, this is our critical member for the beam 218, and for the axial force is 215.415. So, we will going to the calculation of bottom chord. So, NED from software analysis intention. So, we satisfied that NED per NTRD less than 1.0. So, NED is equal NTRD, where AFY per YMO. So, we can get A is equal 783.33 millimeter squared. So, we use size 125 multiplied by 75 multiplied by 8L of an equal angle. Gross area we get 1550 millimeter squared, which is more than 783.33 millimeter squared is from table of properties. So with verification NPLRD AFY per YMO we get 426 kilonewton. So NURD is equal 0.9 A net FU per YM M2. Class 4.13, we know that A net is equal A. So we get 480 kilonewton. So NTRD is equal 480 is greater than NED 215.415 kilonewton. So it's okay. So we assume both is 22 millimeter. DO is equal 22 plus 2, we can get 24 millimeter. So we use the formula 2.5 DO, we can get 60. 5 DO we get 120, and PL is equal 14T. T is we get in the use size 8. Then we get 112 millimeter. So it's beta 3. Beta 3 is the formula. We get 0.673 is a maximum spacing. So NURD beta in net FU per YMY. A net is we use the formula A minus TDO. So we get 1358 mm squared. So we get 314 kilonewton is greater than NED 215.415 kilonewton. So the proposed size is acceptable. So it's okay for the calculation of bottom chord. So we go to the roof truss of top chord calculation. So this is step pro data. This is critical member in the beam 234 in top chord. The axial force kilonewton in 417.979. So we go to the calculation of top chord. So NED from the software analysis in compression, when we use size same as the bottom chord, this section properties is table we get in table of properties, which is H is 1 to 5, B 75, T 8, area 550 millimeter squared, IZ 20.9 mm, IY is 40.0 mm. So the class of section in uniform compression, epsilon is equal square root of 235 per Fy. So Fy, our Fy if 275 is we can get 0.92. For the formula, H per T is equal than 15 epsilon. So we can get H per T is 15.6 is greater equal than 13.8. Also B plus H per 2T we get is less than 11.5 epsilon, when we can get 12.5 greater than 10.58. So the section class is 4. For the resistance of cross section, NCRD per AFY per YM2 is equal 1550 times 275 per 1.0 times 10 of power of negative 3. We get 426 kilonewton. For the buckling resistance of member in plane of thrust LCR, we get 1. L we get from the step flow data when we calculate, and then we get 1.301 meter. So this is formula of MBZRD. This also the lambda is equal radius um, square root of E per Fy. E is 210000 per 275. We can get 86.8. So the lambda 2 is, when we calculate, we get 0.00072 or 7 times 10 power of negative 3. So this we use delta 0.34, we get 0.466. For the x, this the our calculation, then we can get 1.073. So the MBZRD x a Fy per y my, we calculate, then we get 457.37 is greater than NED, which is 417.979. So the proper size is acceptable. So it's okay for the top chord calculation. So thank you.
My name is Nur Syahira binti Muhammad Nizam. I will talk about diagonal brace member in roof truss. The beam number 269 with length of 1.74 meter is chosen as the diagonal brace member in this manual calculation. The axial force on this beam is 173.27 kN and the size used is 125 multiply 75 multiply 8L of unequal angle. The section properties for this size was taken from Eurocode 3. For this member, we have calculated a class, the resistance of the cross-section and the buckling resistance of member for both in-plane and out-plane of truss. In the calculation, we have found that the section is class 4 and the resistance of the cross-section is 426 kN. For the buckling resistance calculation, firstly, we have to know its types of buckling, curve, and its imperfection factor. So, for both in-plane and out-of-plane truss, the buckling curve we get is buckling B and the imperfection factor is 0.34. So we have calculated the design buckling resistance of compression member in plane of truss is 290 kN. Then the axial force was divided with 290 kN for checking. So we get 0.6, which is less than 1. So this value design is passed. After that, the same step was also applied for the outplane of truss, which then we get 375 kN, and it also passed for the checking. So the size of 125 multiply 75 multiply 8L in grade of S275 still is acceptable.
Nur Syafika binti Ahmad Nuruddin, and I want to talk about the roof truss, which is vertical brace member. Firstly, this is a set pro data that we get. For axial force for vertical member is 66.77, and this is an example of vertical member at the roof. To design a vertical member, I use this specification to calculate the vertical design member. Firstly, I design offered internal member by using the maximum tension force and maximum compression force value. Firstly, by using tension member, I use formula NED over NTRD is less than 1.0. After that, I use formula NED equal to NTRD equal to AFY over gamma M naught. So I get the A value, which is 196 millimeter. After that, I use size 125 times 75 times 8 of square hollow section, which is cross area is 1550 is larger than 196 millimeter square. After that, I use the formula NTRD is equal to AFY over gamma M naught. I get the value is 53.9 kilonewton. And then use the formula NURD, which is 0.9 A net FU over gamma M2. And I get the answer is 57.86 kilonewton. So we verify it again by using the formula NED over NTRD, which is we get the 0.9 and less than 1.0. So the result is okay and the proposed size is accepted. After that, I use the formula compression member incline, and I use the NED value, which is 53.840, and use size 125 times 75 times 8, same as tension member. Okay, firstly, get class of a section in uniform compression by using the formula. Epsilon is in the root of 235 over Fy, and I get 0.9. Okay, from the table 5.2 sheet 1 of 3, I get the value C over T is 15.63 and the gamma is 0.21. Okay, so I get the class 1, which is gamma is 0.5, which is 0.21 is lesser than 0.5. After that, use the formula C over T less than 36 epsilon over gamma, and the answer is 157.71. Okay, after that, after we use class of section, we calculate the resistance of cross section by using the formula NCRD is equal to AFY over gamma M naught, and get the answer is 426.25 kilonewton. To design buckling resistance of compression member, I use the formula NBRD is equal to lambda AFY over gamma M1, and I get the value is 426.3. After that, okay, we use this formula lambda, delta, and lambda to get the design buckling. And we after that, for formula NCR is equal to pi squared over EI over L squared CR, and get the value 2.94. Okay, after that, LCR is 1.0 times L, which is we get the 1744 millimeter, and the data is 0.21. After that, formula lambda is in the root of 1550 times 275 over 2.94. We get the answer is 2.22. Okay, after that, use the data formula, which is 0.5 in the bracket 1 plus 0.21 times 2.22 times 10 in the power of 11 in the power of 9 negative 9 minus 0.2 plus 2.22 times 10 in the power of negative 9 squared. After that, we get the formula we get the value is 0.479. Okay, after that, after we get all the value, we insert into this formula. Okay, 1 over 0.479 plus in the root of 0.479 squared minus 2.22 power of negative 9 squared. So the answer is 1.04. So the lambda must be less than 1.0. So 1 is lesser than 1.0. We verify it again by using NED over NBLD is equal to 0.126, which is lesser than 1. So it is okay. And then we verify it again by using NBLD, which is 426.25 times 10 cubic, larger than 53.840, so it is okay. So we use 125 times 75 times 8 in grade of S275 still. That's all, thank you.
Next is the calculation of the critical column. The critical column that were found in our state pro design is column beam number 36 with length of 3.5 meter and its axial force was 188.91 kilonewton. For this critical column calculation, firstly we have to calculate a cross-section classification for flange and web. So by using the proposed size, which is UC 254 multiplied 254 multiplied 89 with steel grade of S275, the cross-section for flange is class 1 and for the web is also class 1. So we concluded the overall cross-section classification is therefore class 1. After that, we have calculated the cross-section of compression resistance, which we get 3,108 kilonewton, and it is more than the axial force. So this calculation has passed. Next is slenderness for flexural buckling. We get this value by using the formula for slenderness. The slenderness that we get from lambda z is 0.52 and from lambda y is 0.31. Lastly, we have calculated the buckling resistance of the member. In this part, we have found that the buckling curve is buckling C and the imperfection factor is 0.49. By using both slenderness value lambda z and lambda y, we have calculated that the buckling resistance of a compression member for NBRDZ is 2610 kN and for NBRDY is 2890 kN. Then the axial force value were divided with each of these value, which then we get 0.07 for both answer. This shows that both value has passed as it is less than 1.0. Therefore, it is concluded that using 254 multiplied 254 multiplied 89 UC in grade S275 still is suitable for the critical column design.
This is Nurul Ifardini binti Narasmadi. I will talk about connection. For the connection, we have chosen a connection of end plate for beam to column and base plate for truss to column connection. For the beam to column, we choose the longest beam, which is beam number 53 with 6.2 meter for its length. For this bolted beam, we need firstly to check the positioning of hole for bolt. We design the diameter of bolt, which is 16 mm, diameter of bolt hole 18 mm, and distance 30 mm, edge distance 35, pitch 50, gauge 70, and thickness of end plate 10 mm. Next, we check for the end and its distance, whether it is suitable or not, and their spacing. For this design, we get pitch and gauge is lesser than 140 mm, which is okay for its spacing. Next, we check for the bearing resistance and shear resistance. So then we get the shear, which is 670.44 kilonewton. After that, we check for the resistance of welded, as you can see in the diagram. Lastly, after all have been calculated, we know that for failure, two planes have to shear. Hence, shear resistance at end plate, which is 593.9 kilonewton. For the selection of truss, we use area that have more trusses. The value of axial force is 12.610 kilonewton and value of shear force is 5.0 6.290 kN. For this design of plate connection from truss to column, first we need to check for its required area. We design the area of base plate, which is 40,000 mm². Next, we check for the effective area and we assume that there is no overlap. We use the formula of A effective equal to 4C squared plus C perimeter column. Then we get C equal to 26.42 mm. To ensure that there is no overlap, C has to be less than half the depth between flange. Next, we check for the plate thickness, whether it is suitable or not to be used. And lastly, we check for its wear. If it is more than BED, the design is okay and can be used. That's all from us. Thank you.